In the autumn of 1942, somewhere deep inside a converted building on Georgia Avenue in Silver Spring, Maryland, a physicist sat surrounded by shattered glass, not from a window, not from an explosion, but from something far smaller and far more consequential. He was staring at the wreckage of another failed vacuum tube, a tiny glass bulb no bigger than his thumbnail that had been designed to survive one of the most violent environments ever engineered by human hands. It had been loaded into an artillery shell, fired from a naval gun at roughly 2,800 feet per second, and spun at 25,000 rotations per minute by the rifling inside the barrel. The forces involved were staggering. 20,000 times the force of gravity, compressed into a fraction of a second, transmitted through the body of an object the size of a man's fist. The tube had not survived. Neither had the dozens before it. The physicist in question was Merle Tuve, and the thing he was trying to build was not just a fuse. It was, if his team could pull it off, the invention that would change the mathematics of aerial warfare forever. And the strangest part of that story is not that it succeeded. It is how close it came to being dismissed as impossible before it ever really began. To understand why the proximity fuse mattered, you have to understand the problem it was solving. Anti-aircraft gunnery in the early years of the Second World War was, by any honest accounting, almost completely ineffective. The numbers are stark. In 1942, the United States Navy fired more than 8,500 rounds of 5-inch anti-aircraft ammunition for every enemy aircraft it destroyed. Gunners aboard ships like the destroyer USS O'Brien and the carrier USS Wasp, ships that were ultimately lost to enemy action in the Pacific, blazed away at attacking Japanese aircraft with everything they had. The sky above Allied convoys was sometimes black with bursting shells, and the results were dismal. The problem was not the guns themselves. The 5-inch 38 caliber naval gun was an excellent weapon, accurate, fast-firing, powerful. It could throw a shell well over 10 miles into the sky. The problem was timing. A shell that did not strike an aircraft directly was useless. It would fly past its target and continue upward until a mechanical time fuse, a tiny clockwork device set by the gun crew before firing, triggered the explosion. Get the timing wrong by even half a second, and the shell detonated harmlessly hundreds of feet from the aircraft. And in the chaos of a battle, with aircraft banking and diving and changing altitude constantly, getting the timing right was more a matter of luck than skill. Artillerymen had dreamed of a better solution since before the First World War. The ideal fuse would sense when it was close to a target and detonate on its own, without requiring the gunner to predict exactly where the aircraft would be at the moment of explosion. This concept, sometimes called a proximity fuse, sometimes a variable time fuse, deliberately misnamed to confuse enemy intelligence, had been discussed in engineering circles for decades. The problem was always the same. To build a fuse that could sense its own proximity to a target, you needed electronics. And electronics in the 1930s and early 1940s were large, fragile things built around glass vacuum tubes the size of light bulbs. Cramming a working radio transmitter and receiver into the nose of an artillery shell, and then making that system survive the catastrophic forces of being fired from a gun, seemed so absurd that most serious engineers had quietly put the idea aside as technically impossible. What changed in 1939 and 1940 was the collision of two things: genuine desperation and extraordinary scientific talent. The British had begun their own proximity fuse research at the Telecommunications Research Establishment, the same laboratory where Robert Watson Watt was pioneering radar, where work on the chain home detection network was laying the groundwork for the Battle of Britain, and where engineers were simultaneously developing the cavity magnetron that would later transform Allied radar capability entirely. The men working on the fuse concept there included Samuel Curran, William Butemant, Edward Shire, and Amherst Thompson. Their approach centered on something elegant in its simplicity. a small Doppler radar built into the nose of the shell. The device would transmit a continuous radio signal outward. When that signal reflected off a nearby aircraft and returned to the shell, the difference in frequency between the outgoing and incoming signal, a phenomenon called the Doppler effect, the same principle that makes a train whistle change pitch as it passes you, would trigger an electrical circuit that fired the detonator. The aircraft would bring about its own destruction simply by reflecting a radio wave. The concept worked on paper. It worked with reservations in early British tests on unguided rockets, which experienced relatively gentle accelerations compared to artillery shells. But British scientists remained deeply uncertain whether the electronics could survive the violence of being fired from an anti-aircraft gun. John Cockcroft, the same John Cockcroft who would later win the Nobel Prize for splitting the atomic nucleus, who had worked alongside Ernest Rutherford at the Cavendish Laboratory in Cambridge, began a parallel effort at Pi Limited in September 1939, trying to develop robust electron tubes that could withstand the forces involved. His team struggled. The tolerances were almost impossibly tight. Every configuration they tried shattered or failed under the shock of simulated firing. The British effort stalled not for lack of ingenuity, but for lack of time. They had a war on their doorstep. Their cities were being bombed. Their factories were working around the clock building Spitfires and Hurricanes and Lancaster bombers. The proximity fuse project, however promising, was not the most urgent thing on the desk of every engineer in Britain in 1940. And so, in the autumn of that year, the British did something remarkable. They packaged everything they knew about the proximity fuse, every circuit diagram, every test result, every theoretical approach, including Buteman's schematic design for the Doppler radio fuse, and they gave it to the Americans. This was part of the Tizard mission, named after the British scientist Henry Tizard, a transfer of British military research secrets to the United States that included not only proximity fuse data, but also cavity magnetron technology, early jet engine work, and crucial radar development. It was one of the most generous acts of scientific collaboration in the history of warfare. Britain was essentially handing over years of research and asking America to run with it. The question was who would do the running. The answer came through Vannevar Bush. Bush was an electrical engineer from MIT, a calm, methodical man who had proposed to President Franklin Roosevelt the creation of a National Defense Research Committee, a body that would link American academic science directly to the military's most urgent technical problems. Roosevelt had reportedly approved the proposal in minutes, and the committee was formed in the summer of 1940. Bush divided it into sections, each responsible for a different family of technical challenges. The proximity fuse problem landed in Section T, the T standing for the name of the man Bush chose to run it, Merle Tuve. Merle Tuve was not a household name in 1940, but he was one of the most respected physicists in America. He worked at the Carnegie Institution's Department of Terrestrial Magnetism in Washington, a building that had originally been built to study the Earth's magnetic field and had evolved into a laboratory for nuclear physics research. Tuve had done foundational work on radio propagation, had contributed to early particle accelerator research alongside Ernest Lawrence, who was building cyclotrons at Berkeley, and had collaborated with Gregory Bright on a technique for measuring the altitude of the ionosphere using radio pulses, a technique that was, in its basic principle, essentially proto-radar. Tuve understood radiophysics at a deep level. He understood vacuum tubes, circuits, signal behavior, and he understood, with unusual clarity for a physicist of his era, how to organize people around an engineering problem rather than a theoretical one. When Bush handed Section T to Tuve in August of 1940, and it was not a random assignment, it was a calculated bet on the right man. Tuve assembled his team at the Carnegie Institution and immediately set about reframing the problem. The British had provided circuits and concepts. What was needed now was not more theory, but working hardware. Tuve ran his laboratory with an almost aggressive practicality. He did not want seminars. He did not want position papers. He wanted prototypes. He wanted things that could be fired out of a gun without disintegrating. And he wanted them as quickly as possible because in the Pacific and Atlantic, Allied ships were dying at a rate that made every month of delay count. His scientists were drawn from physics departments and radio engineering firms and hearing aid manufacturing companies. The last of these more relevant than it might sound, because the miniature vacuum tubes used in hearing aids were the closest thing that then existed to the tiny rugged tubes the Fuze would require. The vacuum tube problem was the central obstacle, and it dominated the early months of work. A standard radio tube of 1940 was a fragile glass bulb, perhaps 4 or 5 inches tall. A hearing aid tube was smaller, maybe an inch in diameter, often less, but it had been designed to sit in a quiet room inside a person's ear canal, not to be accelerated from rest to nearly 3,000 feet per second in the length of a gun barrel. When Tuve's team loaded even the most robust existing miniature tubes into test shells and fired them, the results were the same every time. The tubes shattered. The glass envelopes cracked under the setback force, which reached 20,000 times the force of gravity in the first millisecond of firing. The filaments inside were designed to remain at precise geometric positions inside the vacuum. Under 20,000 G, they simply moved. The electrical connections failed. The circuit died before the shell had even cleared the muzzle. The man who eventually solved this problem was James Van Allen. Van Allen was 28 years old when he joined the Applied Physics Laboratory in 1942. A physicist from Iowa who had been studying nuclear physics and cosmic ray research, he would later become famous for an entirely different discovery. The bands of radiation surrounding the Earth that bear his name, identified using instruments aboard the Explorer 1 satellite in 1958, America's first successful artificial satellite. But before he mapped the Van Allen radiation belts, Van Allen spent the better part of a year working with the Sylvania Company and other electronics manufacturers to develop a vacuum tube that could survive being shot from a cannon. The work was painstaking and methodical. Every design change was tested by firing. Every test generated data on where the failure had occurred. Van Allen and his collaborators redesigned the internal geometry of the tube, changed the way the glass envelope was bonded to the metal base, altered the support structure for the filament, tested new materials, adjusted tolerances. Slowly, the failure rate came down. The tubes became progressively more rugged. And then, after nearly a year of iterations, they had something that worked. A miniature glass vacuum tube, roughly the size and shape of a pencil eraser, that could survive being fired from a 5-inch naval gun and continue operating reliably in flight. 5 of these tubes went into the finished proximity fuse, along with roughly 125 other miniaturized electronic components. The entire assembly had to fit inside a space no larger than a man's fist, mounted in the nose of a standard 5-inch shell. The radio circuitry was built around the Doppler principle that the British had identified. The fuse transmitted a continuous radio signal outward from the spinning shell at a specific frequency. When that signal struck an aircraft and reflected back, the high relative velocity between the shell and the aircraft, both moving fast, in opposite or crossing directions, shifted the frequency of the returning signal slightly. The fuse's receiver detected this frequency shift, and when it crossed a specific threshold corresponding to an aircraft within approximately 70 feet, completed a circuit that fired the detonator. The shell did not need to strike the aircraft. It only needed to pass close enough for the shrapnel pattern, a lethal sphere of steel fragments, to reach the target. There was also a self-destruct feature. If the fuse failed to detect a target within a set flight time, it detonated on its own, ensuring that dud shells would not sink to the ocean floor intact, where enemy divers might retrieve and reverse engineer them. That last concern was not theoretical. It drove the Allied command to make one of the most militarily frustrating decisions of the entire war. The proximity fuse, by early 1943, was ready. Tests conducted aboard the cruiser USS Cleveland in August 1942 had been spectacular. 3 radio-controlled drone aircraft destroyed with just 4 proximity-fused shells. The test canceled early because there were no more drones left to shoot down. The fuse worked. It worked dramatically. And yet the military planners refused to allow its use over land. The reason was fear of capture. If a dud shell fell in German or Japanese-controlled territory, and enemy engineers recovered the fuse, the technological advantage would vanish. The Germans had already demonstrated extraordinary skill at reverse engineering captured Allied equipment. The cavity magnetron, the Norden bomb sight, American radar sets, all had been analyzed and copied to varying degrees. A proximity fuse that fell into a German ordnance workshop might, within months, be turned against Allied aircraft. And so the decision came down from the combined chiefs of staff. The fuse could be used at sea, where dud shells would sink beyond recovery. It could not be used over land. This restriction enraged Army commanders in Europe, who had watched the fuse demonstrate its potential against German V-1 flying bombs over the coast of England, and could only watch while their own field artillery continued firing conventional time-fused shells that were 1/3 as effective. But the naval theater was where the fuse made its first and most dramatic mark. The first combat kill came on the 5th of January 1943, as a United States Navy task force, 7 cruisers and their destroyer escorts, was returning to Guadalcanal after a bombardment mission against Japanese airfields on New Georgia, one of the Solomon Islands. The same island chain where Henderson Field, the airstrip that Japanese and American forces had fought over for months in one of the war's most grinding campaigns, was located. 8 Japanese Aichi D-3A dive bombers, the type Allied pilots called the VAL, a biplane-era design already considered obsolete but still capable of accurate dive bombing, attacked the formation. One of the VALs scored a hit on the New Zealand light cruiser Achilles, the light cruiser USS Helena, the same ship that had survived the attack on Pearl Harbor in December 1941 by the narrowest margin, the ship whose men had seen the torpedoes streak past and heard the explosions across the harbor, opened fire with her 5-inch guns on the departing bombers. The anti-aircraft control officer, a lieutenant known to his crew as Red Cochran, swung the aft 5-inch battery onto the retreating aircraft and fired. 3 salvos. No complicated time fuse setting, no prediction calculation, no attempt to solve the 4-dimensional geometry of an aircraft's future position. The shells flew toward the aircraft, sensed the aircraft, and detonated. 1 VAL fell from the sky in flames and crashed into the sea. It had taken 30 months of scientific labor, 20,000 shattered vacuum tube prototypes, $1 billion in eventual production costs, the scientific heritage of the Tizard mission, the organizational genius of Vannevar Bush, the experimental persistence of James Van Allen, and the operational focus of Merle Tuve to produce that single moment. A Japanese aircraft destroyed without being touched by the shell, destroyed by a radio wave and a fragment cloud. The effect on the mathematics of anti-aircraft fire was immediate and measurable. In 1943, American naval guns fired 9,128 rounds of 5-inch ammunition using proximity fuses and achieved 61 kills. That works out to approximately 155 rounds per aircraft destroyed. In the same period, conventional time-fused 5-inch shells required 508 rounds per kill. The proximity fuse made the same gun more than 3 times as effective without changing the gun, without changing the shell, without adding a single extra sailor to the crew. The only difference was the device in the nose. By the end of 1943, although proximity-fused ammunition accounted for only about 25% of the 5-inch rounds fired by American naval guns, it was responsible for 51% of all enemy aircraft shot down. The Navy had seen enough. Production was accelerated. The production story is its own remarkable chapter. Building 20 million proximity fuses, The eventual wartime total required mobilizing an industrial sector that had no obvious connection to weapons manufacture. General Electric, RCA, Raytheon, Sylvania, Westinghouse, Eastman Kodak, Zenith, Philco, and Crosley were contracted to build Fuze components. Wurlitzer, a company best known for manufacturing organs and jukeboxes, built Fuze housings. The supply chain ran through more than 2,000 firms and subcontractors, ranging from precision machining shops to chemical powder manufacturers. At peak production in 1945, American factories were assembling 70,000 proximity fuses every single day. But the cost per fuse had fallen from $732 in 1942 to $18 in 1945 as the production lines refined their processes and economies of scale took hold. The entire project cost roughly $1 billion 1940s dollars, approximately $15 billion in modern terms. The Manhattan Project cost $2 billion. The proximity fuse cost half as much and arguably killed more enemy combatants. It was also, uniquely among major wartime inventions, one that required the creation of entirely new manufacturing methods. The miniaturized vacuum tubes had never been mass-produced before. The printed circuit techniques used to assemble the fuse's electronics were among the earliest applications of what would become standard practice in the electronics industry. The Fuze forced American industry to solve problems of miniaturization, precision assembly, and quality control at scale that the pre-war electronics sector had never confronted. The engineers who built hearing aid tubes before the war found themselves running production lines that were, by 1944, among the most technologically sophisticated manufacturing operations in the world. Fuze's laboratory maintained an aggressive quality control program, shutting down entire production facilities when defect rates exceeded acceptable limits, dispatching teams to plants to diagnose and correct problems, maintaining what amounted to a continuous feedback loop between the frontline combat data and the factory floor. As the Pacific War intensified through 1943 and 1944, the proximity fuse became increasingly central to the survival of Allied naval forces. The Battle of the Philippine Sea in June 1944, known to American sailors as the Great Marianas Turkey Shoot, saw American carrier task forces devastate Japanese naval aviation in a single day of air combat. The Grumman F-6F Hellcat, the fighter that the American carriers relied on to intercept incoming Japanese aircraft, was formidable, but the layer of anti-aircraft fire that the ships themselves put up, now heavily laced with proximity-fused shells, formed a killing zone that Japanese aircraft struggled to survive. The F-6F's pilots, who scored victories above the fleet, did so against an already attenuated Japanese attack, culled by the gunfire below them. The two systems, fighter defense and anti-aircraft artillery, worked together in a way that multiplied the effect of each, and then Japan changed its tactics. The proximity fuse's very success contributed to one of the darkest decisions of the Pacific War. As conventional bombing and torpedo attacks became increasingly suicidal against the increasingly effective American anti-aircraft screen, Japan's military planners concluded that the only way to guarantee that a pilot's life resulted in ship damage was to make the pilot and the aircraft themselves the weapon. The kamikaze program, formally inaugurated in late 1944 under Vice Admiral Takejiro Onishi as the Special Attack Corps, sent aircraft directly into Allied ships at full throttle, aiming for the flight deck and the hull. Then the success of the proximity fuse, by making conventional air attacks so deadly, had forced the Japanese toward a tactic that was more difficult to defeat with the same technology. A kamikaze pilot who kept flying until impact could not be deterred by near misses. You had to destroy the aircraft completely, not just damage it enough that a rational pilot would break off. This placed new demands on the fuse. The lethal fragment pattern had to hit the aircraft at close enough range to destroy the engine, damage the control surfaces, break the structural integrity. Not just wound the pilot, who would no longer change course. The fuse was adapted. Burst heights and sensitivity thresholds were adjusted for the different targeting problem. Even against kamikazes, the proximity fuse proved essential, like the 7.5 months from the Battle of Leyte Gulf in October 1944 to the end of the Pacific War in August 1945, saw more proximity-fused 5-inch ammunition expended than in all the previous years of the war combined. More than 200 kamikaze aircraft were destroyed by proximity-fused anti-aircraft fire in those final months. The Okinawa Campaign, one of the bloodiest amphibious operations of the entire war, a grinding battle on land accompanied by the largest and most sustained kamikaze offensive of the conflict, would have been catastrophically worse for the Allied fleet without the fuse. Ships like the Essex-class carriers and the battleships of the American Fast Carrier Task Force, and of vessels that formed the backbone of the Pacific offensive, and that Japan was desperately trying to cripple before any invasion of the home islands, were protected by anti-aircraft systems that the proximity fuse had transformed from marginal to genuinely lethal. But while all of this was happening in the Pacific, the Army commanders in Europe were watching with something close to fury. They had developed proximity fuse versions for their own artillery, the 105mm howitzers and 155mm guns that were the backbone of American land-based fire support. By mid-1944, the Army had effective proximity fuses for most of its major artillery calibers. The shells had been codenamed Fuze. Millions of them were sitting in depots in Britain and France waiting, and the ban on land use held month after month, driven by fear that a dud shell on a European battlefield would be immediately recovered and rushed to a German laboratory. The German engineers at Rheinmetall-Borsig, who had actually done their own early proximity fuse research in the 1930s, before abandoning it as impractical, might recognize what they had found. That could not be risked. The situation changed because of the V1, the German Fieseler V103, which Allied forces called the V1 or the buzz bomb, was a pulse jet-powered flying bomb that began striking London and southern England in June 1944, 1 week after the D-Day landings. The V1 flew at low altitude, typically between 2,000 and 3,000 feet, at roughly 350 miles per hour. It was not a high-performance aircraft. It could not evade. It could not maneuver. It flew in a straight line at a predictable height and speed. Against conventional time-fused anti-aircraft guns, it was a difficult target, largely because the timing problem remained. Against the proximity fuse, it was ideal. On the 12th of June, 1944, the Allies authorized proximity fuse use over land in England, specifically for anti-aircraft defense against the V1, a grudging partial exception to the ban, justified because the V1 campaign was killing British civilians at a rate that outweighed the risk of capture. The British deployed their 40mm Bofors guns and their 3.7-inch heavy anti-aircraft guns, along with American 90mm guns, in a dense belt along the coast of Kent and Sussex. Much Winston Churchill personally authorized Lancaster bombers to fly priority cargo flights from Cincinnati to Britain carrying the fuses. The results were almost immediate. The proportion of V1 flying bombs destroyed by the coastal gunbelt rose from 17% in the first week of the campaign to 74% by August, reaching 82% on the single best day of the defense. One anti-aircraft unit in Antwerp, where the V1 threat extended the program into Belgium later in the war, destroyed 48 of the first 75 V1s it encountered after being equipped with proximity fuses. The port of Antwerp, a critical Allied logistics hub through which the supplies needed to sustain the final offensive into Germany were flowing, remained open. The proximity fuse had saved it. The V1 threat, which had been causing genuine strategic disruption to the Allied supply chain and immense suffering among the civilian population of southern England, was broken as a decisive weapon by the combination of fighter interception, barrage balloons, and above all, the proximity-fused anti-aircraft gun line along the coast. And then came the Ardennes. On the 16th of December, 1944, Germany launched its final major offensive on the Western Front. 21 divisions, including elite panzer formations like the 1st SS Panzer Division, Leibstandarte SS, Adolf Hitler, and the 5th Panzer Army under General Hasso von Manteuffel, broke through the thinly held American line in the Ardennes forest of Belgium and Luxembourg, aiming to split the Allied armies, capture the port of Antwerp, and force a negotiated peace. The Battle of the Bulge, as it became known, was the largest land battle ever fought by the United States Army. 250,000 German troops against approximately 600,000 American soldiers in the most brutal winter conditions the Ardennes had seen in decades. Frozen ground, blizzard visibility, roads blocked by snow and wrecked vehicles, German Panzer IVs and the fearsome Tiger II tanks grinding forward through the frozen forest, while American infantry units like the 101st Airborne Division held their positions at Bastogne. General Dwight Eisenhower, Supreme Allied Commander, understood what he was holding in his ammunition depots. 200,000 shells with posit fuses, cleared for naval and coastal anti-aircraft use, but still banned from direct use in land artillery against ground troops. He demanded the ban be lifted. The logic was simple and urgent. The Germans had broken through in bad weather that grounded Allied air power. The air cover that had made the Allies so dominant in the summer and autumn of 1944 was gone. Artillery was what remained, and the proximity fuse would make that artillery dramatically more lethal against massed infantry and armor than anything previously available. Within 2 days of the German breakthrough, the ban on land use was lifted. The posit shells were distributed to American artillery units. The German engineers who captured an American ammunition dump containing 20,000 proximity fuses during the confusion of the early offensive never recognized what they had found. They had previously concluded that a proximity fuse capable of surviving gun launch was physically impossible because the accelerations involved exceeded what any electronic device could withstand. Faced with an actual working example, they did not identify it as such. The proximity fuse's effect on ground operations in the Ardennes was felt almost immediately. Unlike conventional artillery, which fired either contact-fused shells, rounds that buried themselves in snow or frozen earth and directed their fragment energy downward before detonating, or time-fused shells that were difficult to set accurately in bad weather without observation, the proximity-fused shell detonated in the air above its target. At the optimum burst height of around 30 feet for a 105mm shell, the fragment pattern covered an enormous area, roughly 3,000 square feet, compared to the 60 square feet covered by a conventional ground burst. A German infantry unit in a shallow foxhole was protected from a contact burst that hit nearby ground. It was not protected from a burst that detonated 30 feet above its head and rained shrapnel downward at an angle that no earthwork could stop. General George Patton, commanding the Third Army, wrote a letter to the War Department that became one of the most quoted assessments of any single weapon in the entire war. Patton's units had caught a German battalion attempting a river crossing of the Sauer River. Our single battalion concentration of proximity-fused artillery fire, lasting a matter of minutes, killed 702 confirmed enemy soldiers. Patton called the fuse devastating and stated flatly that when all armies had it, an entirely new method of warfare would be necessary. He credited it with saving the city of Liège. German prisoners taken during the Ardennes campaign described the experience of proximity-fused artillery fire in terms that underlined the psychological as well as physical effect. There was no defense, one prisoner reported. The shells came from nowhere. Men who had survived direct artillery barrages by lying flat in foxholes found that proximity bursts followed them down, in even log-reinforced revetments, the improvised overhead cover that infantry had learned to build in the Italian campaign against German Nebelwerfer rocket fire, did not stop the downward-raking fragment pattern. The German field commanders knew they were facing something new. Their radio intercepts referenced a mysterious type of shell that behaved differently from anything previously encountered. but they could not identify the mechanism and had no counter. Through the final months of the European War, from the Battle of the Bulge to the crossing of the Rhine in March 1945, through the drive into Germany that followed, proximity-fused American artillery continued to add its murderous effectiveness to the advance. In those same 3 months, anti-aircraft batteries using proximity fuses brought down more than 1,000 German aircraft over the European theater. The Messerschmitt Me 262, the world's first operational jet fighter, fast enough and agile enough to evade conventional anti-aircraft fire in many engagements, was still within the lethal envelope of proximity-fused batteries when it attacked low-level targets or attempted to intercept Allied bombing formations at predictable altitudes. The fuse did not discriminate between piston-engine aircraft and jets. It only required that the aircraft pass close enough to reflect a radio signal. When the war ended in September 1945, the accounting was done. More than 22 million proximity fuses had been manufactured at a cost of over $1 billion. The fuse had been adapted for 28 different gun types across the Allied forces, from British Bofors guns and American destroyer main batteries to Army howitzers and shore-based heavy anti-aircraft pieces. It had effectively tripled the lethality of naval anti-aircraft fire, quadrupled it against certain target types, and transformed ground-based field artillery into a weapon that could kill in the open what previously only direct hits could reach. The United States Navy's own official figures confirmed what every gun crew already understood, that a 5-inch shell fitted with a proximity fuse was roughly 3 times as likely to destroy an enemy aircraft as the same shell fitted with a conventional time fuse, and at the height of the kamikaze offensive in 1945, that ratio was the difference between a ship's survival and its destruction. Secretary of the Navy James Forrestal, surveying the entire course of the Pacific Campaign, said the proximity fuse had helped blaze the trail to Japan. It was not hyperbole. The fast carrier task forces that struck the Japanese home islands in the final months of the war, that enabled the firebombing campaigns and the final strategic assault, were sustained in part by the gun shield that the fuse provided. Without it, the losses to kamikaze attack would have been unsustainable at the operational tempo the Pacific Campaign demanded. Vannevar Bush, who had organized the entire American wartime research program and overseen projects that included early radar work, operational research, and the initial organizational scaffolding of the Manhattan Project, now credited the proximity fuse with 3 distinct strategic effects: the protection of the fleet, the defeat of the V-1 offensive, and the disruption of German ground operations. He placed it alongside radar and the atomic bomb as the most consequential technical achievements of the Allied war effort. The manufacturing legacy was equally profound, though it took longer to see. The forced miniaturization of vacuum tubes and electronic components that Section T had driven through sheer operational necessity created a body of industrial knowledge and factory capability that had not existed before the war. Engineers who had spent 4 years building tiny rugged electronics for artillery shells returned to the civilian electronics industry, carrying methods and intuitions that had been earned through extraordinary pressure. The printed circuit techniques pioneered in fuse assembly moved into commercial radio and television manufacture. The miniaturization of vacuum tubes fed directly into the post-war research at Bell Laboratories that produced the transistor in 1947. James Bardeen, Walter Bratton, and William Shockley, building on a foundation of miniaturized electronics, thinking that the proximity fuse project had helped lay. James Van Allen himself returned from the Unapplied Physics Laboratory to the University of Iowa, where he designed the scientific instruments for Explorer 1, the satellite whose launch in January 1958 made him famous in a way that no proximity fuse could. But the intellectual discipline that had shaped him, the determination to make delicate electronics survive extreme environments, on the obsessive testing and redesign cycle, the fusion of physics and engineering that Tuve had demanded, was formed in the pressure cooker of Section T. the Doppler principle at the heart of the fuse found new civilian lives that the scientists of 1940 would never have imagined. The same logic? Transmit a signal, detect the returning echo, measure the frequency shift, and trigger a response became the operating principle of the automatic door sensor, the motion detector, the vehicle backup radar, the collision avoidance systems fitted to modern aircraft and automobiles. Every time an elevator door pauses because it senses a person stepping through it, every time a reversing car emits a warning beep because its radar has detected an obstacle, the physics of the wartime proximity fuse is present. The technology moved from artillery shells to everyday life in the space of a generation, following the path that miniaturization and transistorization made possible, a path that the fuse itself had helped open. Merle Tuve returned to the Carnegie Institution after the war. He became director of the Department of Terrestrial Magnetism, the same institution where he had assembled the first Section T team in August 1940 and served in that role from 1946 to 1966. He resumed research in nuclear physics, in radio astronomy, in the geophysical sciences that the department's original mandate had covered. He collaborated with colleagues across the post-war scientific community, contributing to the foundational work that defined American academic science in the Cold War era. Some of his former Section T colleagues moved into the new field of communications electronics, where the miniaturization experience they carried shaped the first generation of commercial broadcast and consumer radio technology in ways that the pre-war industry had not been capable of achieving on its own. He was remarkably reticent about the proximity fuse work, not from false modesty, but from something closer to genuine ambivalence. Tuve had spent years driving engineers and physicists at maximum intensity toward a device whose explicit purpose was to kill more effectively. He had done it because he believed the cause was just and the need was undeniable, and because his country had asked him in its most desperate hour. But when it was over, he turned back toward science that illuminated rather than destroyed. He gave few interviews about Section T. He discouraged what he considered excessive celebration of the fuse's lethality. He understood what the device had done, understood it with precise quantitative clarity because he had tracked the kill rates throughout the war, and he was satisfied that it had been necessary. He was less interested in being celebrated for it. The label on the German ammunition dump that captured 20,000 proximity fuses in December 1944 had read, in the hasty translation of a battlefield acquisition, something like unknown artillery shells. The engineers who examined them concluded the fuses were simple time fuses of conventional design. They were wrong. And in being wrong, they failed to recognize the most consequential piece of engineering that had passed through their hands. All their own earlier research at Rheinmetall Borsig in the 1930s had convinced them that a proximity fuse capable of surviving gun launch was physically impossible. That conviction, wrong as it turned out by several orders of determination, meant they held the answer to the problem in their hands and could not see it. That failure of recognition was itself a kind of tribute to the achievement of Section T. They had built something that looked ordinary from the outside, a metal cylinder screwed into the nose of a standard 5-inch shell, unremarkable in appearance, conventional in outline. Everything extraordinary about it was inside, packed into a space smaller than a man's fist, capable of surviving 20,000 times the force of gravity. And then in the cold air above the battlefield, reaching out with an invisible radio hand to sense the presence of an enemy aircraft or an enemy soldier and answer it with fire. The engineers of Section T had set out to solve a problem that the world had said could not be solved. They had solved it, and the world had never been the same since.